Okay, so a compact set it is often seen in the a lot of statements, right? As we see in the microeconomics. Okay, so and that continues. So for okay, so this alpha x prime lies in a compact set of r plus. So this would be a set from alpha 0 to alpha 1. And for all x prime, what is this x prime? It is such that the distance of x prime and x, it has to be less or equal to this epsilon. Okay. So later we'll draw this x prime and this epsilon on this on the diagram that we just had previously. Okay, so let's complete this argument first. And since xn, so the sequence, it converges to x. Okay, so this is the starting point, right? And there exists a some number n, okay, such that this alpha xn, it lies in this compact set for all number n which is strictly greater than this capital N. Okay, but any infinite sequence that lies in a compact set it must have a convergent subsequence. And this will be a result in the mathematical appendix on the textbook, okay, in the section endpoint F. And you could see this argument in that, okay? So now let's complete the figure before we go ahead, okay? So in the little figure that we had here, okay, perhaps we should have another little figure because we're gonna draw something else. Okay, so this would be the two-dimensional x space. Okay, x1 is 2, and let's say this is the 45-degree line of z. Okay, and suppose this would be the indifference curve or the indifference set for x, and let's put this x here, maybe something higher. Okay, let's put this x here. Okay, so let's suppose that this okay, so that epsilon is just some radius that gives a circle or a ball with the center of x and with the radius of this epsilon, okay? This is with length of epsilon. Okay, so at this point it is, as we mentioned, this is alpha e, right? Or alpha x e. Okay, so let's say this alpha 0 is somewhere here. Okay. Maybe we know that this is 45 degrees. Okay, so we don't need that. Okay, so let's suppose this is alpha 0 right here. Okay, and suppose alpha 1 is some point here. Okay, good. So this compact subset of Z is something this. Okay, so let's use a blue color. So this set here. So this would be the compact subset of Z, and with the boundaries of alpha 0 and alpha 1. Okay. And so the sequence, it has a convergent subsequence, and by the monotonicity for any epsilon, this radius positive number, and alpha x prime lies in the compact subset of R plus, which is from alpha 0 to alpha 1, and for all x prime such that the distance between some x prime with this x itself, this distance has to be smaller or equal to epsilon. Okay, and since this sequence xn, it converges to x, there exists some capital N such that this alpha xm lies in the compact set for all the little n, which is greater than this capital N. Okay, and we know that an infinite sequence that lies in a compact set must have a convergent subsequence. Okay, and that is given by some statement in the appendix. Okay, so and next, we're gonna show this right in details. So what remains from here to show is that, okay, to show that all convergent subsequences okay of alpha xn, so the subsequences of that converge to alpha x. Okay, we know that it has it's in the compact set, so it must have some convergent subsequence. And now we're going to show that all the convergent subsequence of that converge to this point that we need, this alpha x or this ux, right? Okay. So to prove this, okay, so we're going to use the contradiction for the proof, and suppose the opposite, that there is some strictly increasing function m that assigns to each positive integer n some positive integer mn, okay, and which is a very long sentence, for which the subsequence alpha x m n, okay, So the subsequence converges to some alpha prime, which is not alpha x, let's suppose. Okay. Let's put this alpha prime x to some point here. Okay. Sorry, alpha prime e. Okay. All right. So we're gonna show the contradiction next. Okay. Now let's suppose the opposite, and we try to get this, hope for this contradiction to show up, right? So next is to show that this alpha, which is greater than this alpha x, this level, and that needs to lead to a contradiction. Okay. So now we're gonna show this. So how to do that? So to begin with, note that the monotonicity implies that alpha prime e is strictly preferred to alpha e, right? Because that is alpha, because alpha prime is strictly bigger than alpha x. So now we simply let some midpoint of alpha prime between the alpha prime and alpha x. Okay, so midpoint would be a half of alpha prime plus alpha x. Okay, let this be the midpoint. So where's the midpoint on the figure? It will be just somewhere here, right? So this would be the alpha hat times e. Okay. All right, so this is the midpoint. And what else? So by the monotonicity again, alpha hat e is also strictly preferred to alpha x e. Okay. Now since alpha x m n, the big thing that we mentioned before, since that converges to alpha, and which is strictly, we said that this is strictly greater than alpha prime. Okay. So because that is strictly greater than alpha, right? So it has to be strictly greater than the midpoint. So there exists some number in upper bar such that for all number n which is greater than that, this alpha x m n is strictly greater than alpha hat. Okay. So hence, for all such number n, okay, so what we have is that little x m n is indifferent to alpha x m n e, right? Because x is indifferent to this alpha e, right? So in the limit, they are indifferent as well, and this is strictly preferred to alpha prime e by the monotonicity. Okay. Right. So this is from monotonicity. Okay. And because the preferences, this is the starting point, right? Because the preferences are continuous. Okay. So the above implies that x is weakly preferred to alpha prime e. Okay? But since that x itself, it has to be if different to alpha e, right? They're at the same indifference curve. So we get altogether alpha e, it is weakly preferred to alpha prime e, and that is exactly the contradiction with just the above statement, right? Okay, so this is a very long proof, but if you read this slowly and you'll just understand and see the underlying intuition of this proof in step by step, right? Nothing is too complicated. It's just a long proof, right? So, and then similar for the other one, right? Similar for ruling out the other possibility that alpha prime is smaller than alpha x. So they has to be equal to each other, right? Okay. Thus, since all convergent subsequences of this alpha x and must converge to alpha x, okay, and then finally we have the limit as n goes to infinity and alpha xn is alpha x itself, okay, and then the proof is complete. Okay, good. So now let's have a very quick look on this proof, and all those longer, this very long proof for this in this part, they're all just to show this contradiction, where we start with assuming this, right? So we assume this, and the opposite of this result that we're going to have, right? And then we lead to this contradiction. And finally, we use this contradiction to show that all the convergent subsequences of that converge to this alpha x itself. Okay, so then we have shown that this alpha, this level is exactly just this one level, right, that we can obtain. Okay, good. So, and then after this, right, after we show this statement, and then we know that this is this completes the second argument, right, where this UT function, it is continuous. Okay, good. So this is very interesting and also a very long proof. Okay, but we could see a lot of interesting, useful statements there that are helpful for us to later to prove things, right, in those analyses. Okay, good. So from now on, then as mentioned in the textbook, we're going to assume that the consumer's preferences, the preference relations are continuous, okay, and then they could represent it by a continuity function. Okay, so and we know that if the preference relation is continuous, then there exists some continuity function representing the preference relation, but not all the T functions representing the preference are continuous, right? And a strictly increasing but discontinuous transformation of a continuity function also represents the preference relation, okay? But those are just some special cases, okay? Good, so, but normally we will have all those things to be continuous, okay? It's just convenient for us to show, to analyze some of the real world scenarios in the consumers, in the demand theories, in the consumers problems. Okay, so, and further, we also, and it's also convenient for us to assume that utility functions are differentiable, right? As we discussed in the beginning of the video, that if we suppose the utility functions are differentiable, then we could take the derivatives of the utility functions and try to solve the optimization problems, right, by taking the derivatives. Okay, so and it is possible, okay, however, for the continuous preferences not to be representable by a differentiable utility function, okay? So, and to give example of some preferences that are not representable, of preferences not representable by differentiable utility function. Okay, and a very simple example is called Leontief preferences. Leontief preferences. Okay, and Leontief preferences, they have those L-shaped indifference curves. Okay, and they have they have those kinks right on the rays, either on 45-degree lines or any other rays starting from the regions, right? Okay, so mathematically for Leontief preference, it is stated as follows. So for x weakly better than x prime, x double prime weakly preferred to x single prime, if and only if we have this minimum of x1. So here again we assume that this is in two-dimensional positive real numbers. Minimum x1, x2 double prime, it is greater than or equal to the minimum of x1, x2 single prime. Okay, and this comes from the kinks of x1 equals to x2. Okay. Okay, so in a figure, now let's draw this Leontief preference. So this is x1, this is x2. Okay. So let's suppose this would be the indifference curve. So this is not straight, but I'm trying to indicate that this is a straight L-shaped curve. Okay. So let's have this point as x prime, and this would be, let's suppose this is the 45-degree line. Okay. And we have another straight, but this curve with the kink, and let's suppose this is the point with x double prime. Okay. All right. So this is just an illustration for the Leontief preference, right? And you can see that all those kinks, those are the places where we cannot differentiate this utility function, right? But those are continuous, of course. Okay, because you could always compare compare those utility functions with very small changes. Okay, and even we can push those little gaps to 0, and they could simply continuously shift from one to each other. Okay, so they're continuous, but there are some kinks which are not differentiable. Okay, and something else that are also somehow important is that the some properties that we mentioned previously, such as the homothetic and quasi-linear, those are not ordinal properties, right? Those are cardinal properties that simply helpful for us to further analyze some problems. Okay, but those are not the ordinal properties that we normally assume when we're trying to construct the utility functions. Okay, so there are some minor differences, but might be useful to notice. Okay, so something at last in this episode, let's try to visualize this utility function. Okay, so we mentioned that from this picture or the other picture in the very beginning of this episode, so we mentioned that this point or this whole level, right, of on this curve, this whole level is the utility function, right? So but that has to be sort of another dimension, right? So how do we represent this dimension of the utility? Okay, but if we want to also preserve, or we also want to show the x1, x2, so how do we do that? And it's very natural to just increase the dimension, right? So we can simply have a 3D, the three-dimensional figure to illustrate the preference. And let's suppose we have, so this is going into the paper, okay? Let's suppose this is x2 and this is x1, okay? And this is the third dimension, which is, this is just a rough idea of this intuition of the utility function, okay? This would be u of x or alpha x, right? Okay, so what we are gonna have, for example, as the utility function, okay, so so let's say a utility with a 0, a level of x1 and 0 of x2, this is 0 utility. Okay, let's start from this point. Okay, and let's suppose with so roughly speaking, what we have in the previous two figures is just a projection of a three-dimensional illustration of the utility function onto a two-dimensional space. Okay, so what we're gonna have is that this is just some rough idea. Okay, so we're gonna have this as some utility function. So this would be just a surface. Okay. All right, and you could try to imagine that this would be some a three-dimensional picture, and this utility, this function, and it goes up as the x1, x2 increase. Okay, and then let's erase those. And what we have normally on this projection of the two-dimensional space is that those indifference curves, right? Let's say this x point is here. Okay, so and let's suppose this is the 45-degree line. Okay, and you could just imagine this as a three-dimensional shape. Okay, and it climbs up, and then it increases as the both axes go up. Okay, and those are when we cut from the third dimension, from the vertical dimension of ux, and those projections are exactly the images or the graphs, the figures that we see in the above those two pictures. Okay, and okay, so and something also useful for us to know is that so the property of the convexity of the preferences, so this convexity also implies that this utility function, as we said, this three-dimensional utility function, it is quasi-concave. Okay, so convex preferences implies quasi-concave utilities. Okay. Okay, so the utility function. So what do we mean by this quasi-concavity? So U is quasi-concave if the set for Y in R plus L dimensional space, if UY is weakly bigger than UX, if this set Y, set of Y, this is convex for all X. Okay. And equivalently, this set is convex if the convex combination of 2 points x and y with the utility is in the utility function which is greater than or equal to the minimum of the ux and uy. Okay, so those two are equivalent definitions. Cool. Equivalently, okay, if u alpha x plus 1 minus alpha y greater than or equal to the minimum of ux and uy for any xy and all the alphas between 0 and 1. Okay, and if the inequality is strict, then this is a strict quasi-concavity. Okay. Good. So we said that this convex preferences, okay, so it implies this quasi-concavity of the utilities. Okay, so from this picture, we could also have some intuition of this statement, right? So it's essentially that if this we said that this preference to be convex, it's simply that the upper contour set of this preference is convex, right? So this set is convex. And in this case, this utility function, as we said in three-dimensional, this utility function itself, it has to be quasi-concave. Okay. Okay, good. But however, we need to notice that the convexity of the so the convexity of the preference relation does not imply a stronger property that the utility function is quasi-concave. It is concave. Okay, so let's write it down. However, convexity does not imply a stronger property concavity for utility. Okay, so the concavity means that u alpha x plus 1 minus alpha y, this is greater than or equal to alpha ux plus 1 minus alpha uy. Okay, so we can already see, and for any xy and alpha. Okay, so from here we can already see the differences between those two statements, right? So in the quasi-concavity, it is this we have this the same in the left hand side here, right? But on the right hand sides, those are different, right? In the quasi-concavity, we have the minimum of u of x and y, but here this would be just a split the ux and uy and multiply by alpha and 1 minus alpha, right? So those two will be completely different. Okay. Good. So this will be everything for before we introduce the utility maximization problem. Okay, in the section 3.d. Okay, so this will be everything for the section 3.c, and where we used all those ordinal properties for the privacy relation, including the rational monotonicity and importantly the continuity to obtain a continuous utility function, which is unique for us to represent the preference relation, a continuous preference relation. Okay, and that'll be very useful for us to further analyze the utility maximization problems in the future. Okay, good.